I'm Sarah Woods, and on behalf of EOL ACOM, I'm pleased to introduce Dr. Laura Pan. Dr. Pan received her bachelor's in physics from Beijing Normal University before obtaining her master's and doctorate in physics from Johns Hopkins University in quantum optics. She went on to hold a postdoc with the physics lab at the National Institute of Standards and Technology in Maryland, after which she held a joint research appointment at NIST Center for Atomic, Molecular, and Optical Physics and University of Maryland's Institute for Physical Science and Technology. From NIST, Dr. Pan took a scientist position working on ozone processing at NASA Goddard before joining NCAR's Atmospheric Chemistry Division, now ACOM. Notably, Dr. Pan's remote sensing and data analysis expertise have been utilized as a co-investigator on the NASA OMI and UARS science teams, as well as in producing Earth system science research using data and products from Terra, Aqua, and ACOM satellites. Dr. Pan has also served as a retrieval scientist for the NASA Meteor 3 TOMS and NASA Terra MOPIT teams. Dr. Pan's UTLS research has integrated airborne studies with satellites and modeling. She served as PI for the UTLS Project Awards from the NCAR Directors Initiative Fund from 2003 to 2013. As part of START-05, she served as the first mission scientist for the first G5 scientific test flight in December of 2005. Dr. Pan has also served as PI and mission scientist for several other field campaigns on the NSF NCAR G5, including Seekers, Contrast, and most recently, ACCLIP. Please join me in welcoming Dr. Pan for her seminar titled Progress Overview of the Asian Summer Monsoon Chemical and Climate Impact Project. Welcome.
Thank you, Sarah, and thank you, everybody, for coming. I expect this to be a mixed audience, that there are people very familiar with the campaign, there are people who are not. So I will start with some general overview. Let's see. Whoops. Always want to update, right? Do you not see that? Okay. Why is it not going? Hasn't worked. Okay, I'll just use the key. Okay, so this is the outline. I will start with the general background of ACCLIP and going pretty fast. Then some simple campaign overview and operational accomplishments, then hopefully spend more time on the new things, what we call the scientific progress, and since the campaign, and the discoveries and the new understandings enabled by the campaign. So this is just a flashcard, really fast. I won't explain that a decade before ACCLIP campaign, and our satellite, the NASA satellite and the other satellite, has identified a very large recurring signature, chemical signature at the troposphere level from the Asian monsoon. So from all kind of species and gas phase and aerosol, and that happens. All these are seasonal or monthly average picture, and this large signature got attention of the atmosphere chemistry community. That is the monsoon has been studied for weather pattern for centuries. Now only this new satellite information excited a new field of study, that is how monsoon is contributing to atmosphere composition and atmosphere chemistry. These satellite data cannot really provide enough information. That's why the field campaign is being planned. So the very first one I was involved, and the first one community planned, is called Seekers. And some of us still remember we worked very hard and organized a campaign, and it did not go in the last minute because the geopolitical of the region, reasons of the region. Then the first campaign, airborne campaign, ever got some information from the Asian monsoon is the OMO campaign using the German G5 HALO and had 2015. And the next one with a lot of large community effort from Europe is using the geophysical in 2017. And then is ACCLIP. It was going to be 19, going to be 20, then the pandemic happened. So after 2 years pandemic, we managed to do it 2022. And following ACCLIP, there's one more campaign from German Hello and downstream to study further of the Asian monsoon. So how would this campaign look together, right? So we have this flat tracks from various campaigns. And it turns out all the campaigns together really complementary to each other. And it show, let me see. Okay, this is working. So in the day-to-day picture, the Asian monsoon UTLS anticyclone showed as a 3 subsystems. So in the center is this Tibetan anticyclone, and the west and the east shedding. That's a dynamic process at the UTLS level, produces this Iranian anticyclone and this Western Pacific anticyclone. So the 3 campaigns really planned to sample all 3 subcomponents, and the FEEDS campaign will do the downstream. So when we plan ACCLIP, the goals and objectives, hypotheses, well stated, just to investigate the impact of the Asian monsoon on transporting the gas aerosol, and how that impact global chemistry, and how that link the surface emission to stratosphere or upper troposphere to impact climate change. So the specific objectives, of course, is to get transport information, to understand how Asian monsoon actually transport as a pathway, and the chemical content from gas phase, and the aerosols, size and chemical composition, and the water vapor. So this is a very fast overview of that. So 2 platforms are involved and working together, complement each other to do this campaign. So people recognize the NCAR, NSF NCAR G5, and this is NASA WB57. So they have different sampling range that complement each other. The G5 can go from the surface all the way, very easily go up and down to near 15 kilometers, I would say. I conservatively say 14.5. And WB57 typically samples, this is not working very well, samples 13 to 19 kilometer altitude. So these large, both of them had a large payload, very extensive, complementary to each, comparable to each other, really covers the large range of gas phase. And it's like state of art, and you have international team joining, bring the best instrument we have for this platform. So these are the flat tracks. So the left one shows in the domain of Asian monsoon, and the transit flight is being shown. It's not going very well, the pointer. And then this vertical sampling range. And the red dots on this vertical one shows where the trouble pulse is. That is, we transition from upper troposphere to lower stratosphere, and mostly is the WB57 samples across the trouble pulse. And the campaign from Osan, it was slightly longer than a month, and there are 29 research flights from all 2 flights together operated directly connected to Osan. So here is the table of the large amount of chemical species and aerosol informations and dynamic variables we sampled from the 2 planes. And this is the largest data set so far at a UTLS level around the Asian monsoon, or almost around any of these Asian region campaigns. So in addition to the airborne, we also have a large collaboration from the regional scientific community and has surface and balloon measurement. So this shows surrounding ocean, and also our NSF team has measurement near ocean and a lot of balloon launches and with the various sensors here. Okay. So all this is really fast. Now I'm wrapping up the overview of the campaign, just some interesting days. This is what NASA built a temporary hangar for the WB-57, locally jokingly called the NASA Taj Mahal. And then the very first week of this campaign, we got hit by a 100-year flooding event locally, and the nearby town, people died. I think like 9 or 10 or a dozen people died. And this the pickup truck shows how deep that is. We stopped flying for at least 4 days. And this is a medium day. We talked with a lot of different reporters on the event, on the campaign. And this is the open house day. A lot of locals, very, very hot day. Locals line up outside the G5, trying to get on to see what the instrument inside look like. And the NASA activity in the tent is also very active. So here we have the group photo. It's a very large team. And this probably only half of the people, just because people come and go, and some work remotely. So, but this is the day we had a large group of people, and reflecting the activity of the time. Okay, now let's talk about the science. And we single out the accomplishment. There's a very significant accomplishment of the operation. That is, we successfully sampled the air mass in the Tibetan anticyclone. So I will spend some time explaining why this is significant. So I talked earlier that the anticyclone on seasonal average is a big oval blob of continental scale, but from day to day, very often appear as 3 subsystems or sub-anticyclones. It doesn't always show up at the same time, but this is MLS carbon monoxide at 150 hectopascal, reflecting a particular day. You will see the 3 anticyclones, Tibetan anticyclone, and the Iranian and the Western Pacific. Statistically, this is how often they occur and which longitude they peak at. So these 3 anticyclones are not equal. This is modeling work to show, if you look at the Tibetan mode, you will see the vertical transport showed up as a chimney behavior, and the convection can go all the way up to the tropopause. And if you look at the other 2 modes, you do not have a bottom. Okay. So the physics behind is the Tibetan anticyclone is the one has all the convection. It's a convective-driven anticyclone. Then the other 2 is really coming from, the content is coming from the Tibetan anticyclone through these dynamic processes of east-west eddy shedding. So this east-west eddy shedding is very well shown by this PV at the 360K figure, that you can see that the Tibetan anticyclone is there all the time, and the east-west shedding happens from time to time. It's a dynamic process. So the year we did the campaign, the operational highlight shows that the year we did the campaign is dynamically anomalous. It's very special. That is, if we see an average anticyclone, and that for 44 years represented by this yellow patch, and that same yellow patch, this is geopotential height at 150 hectopascal, is one of the ways to show what anticyclone is. So the August of our 2022 is represented by this blue. That is 2022, we have a significantly extended and somewhat eastward shifted anticyclone. So that's why when we go there, we really thought we're going to sample the shedding but we get to sample inside of the Tibetan anticyclone. So these are the two flights reflects our operational highlight that we sampled. We actually flew inside of the anticyclone that is shown by the cyan color or magenta color that's as the inner, using PV field to show the anticyclone. So the red marks the G5, the WB, and the white marks G5 flat track. So both on August 15th and August 19th, we have to entirely in the Tibetan anticyclone. That is, it has the vertically transport air mass and that east-west oscillation or the large-scale dynamic shifted that air mass to our direction. Usually it should be over the continent, we will have no access. So it's a very serendipitous and it's toward our favor, so we got it. So also because we had a really good forecast. So these are the forecasts of GEOS FP, that's a Goddard model, it's carbon monoxide. So on these 2 days, you can see the eastward sticking out of heavily polluted anticyclone. So these anticyclone represented by carbon monoxide complements the PV field. That's what we sampled. So continue on that tone, so we're going to come back to that again and again. It's all related. So if I had to summarize the most important accomplishment from science and operation so far, I will divide it into this, I will name it into three. The first one is because of the specific year, and also because the sampling, we discovered or rediscovered the importance of East Asian monsoon. And that later on we'll talk about how that transport has a big impact on the ozone depleting substances. And the second one is we sampled both, being that we can only fly over the northwestern Pacific, and we sampled both South Asian and East Asian convection. So that's a very significant accomplishment, I'll explain. And the last one is we identified monsoon convection is significantly deeper than what is estimated by the models or previously known. So how deep the convections are. So I think from transport point of view, and this 3 point is the most significant one. I'll go back one by one. So in the past, when we sample Asian monsoon, we mostly focused on the upper troposphere anticyclone. So a lot of time called South Asian high by this feature. But specifically, Asian monsoon has subsystems. The two most important subsystems, one is called South Asian summer monsoon. The other is called East Asian summer monsoon. These two subsystems are driven and controlled by different dynamics. I will not explain, just to point out they're different, and each have its own activity center. So the South Asian monsoon activity center is represented by the monsoon trough, and the East Asian is represented by this subtropical front. So East Asian, or a lot of times locally specifically called Meiyue front. So before ACCLIP, and we have done modeling and satellite data analysis for about a decade and published many papers. And when we say Asian monsoon transport, convective transport, we really meant South Asian monsoon, because we think the South Asian monsoon dominated the air mass get into the monsoon anticyclone. So this is just an example, okay? In this figure is a ACOM model carbon monoxide and a chimney behavior right on the southern edge of the Tibetan plateau. We have papers I involved, paper I didn't involve, all showing basically same idea. The region of upward transport focused on South Asian monsoon. So that's why when we decided to go to ACCLIP, it's because we saw this process called eastward eddy shedding. So what is showing on the right panel is the work modeling work done by Jim in the back, and to see if you have a surface idealized tracer, and that is lofted by local convection. You can see this is the 6-hourly going. And then they're unstable at upper level, and the instability creates shedding, and the shedding come exactly the places that we plan to go. We plan to go there because we know we'll get shedding. And that didn't happen. That didn't happen. You know, it's the other side of eastward shedding, eastward shifting, that we got the inner of the Tibetan cyclone, and the shedding went further to the dayline. So we didn't get a shedding, but we rediscovered the East Asian monsoon. So that's what happened. So what happened is, if you look at retrospect, you look at a deep convective cloud from the satellite. So there's a database you can use to see the deep convection for all the cloud above 12 kilometers, the cloud top that had a convection under. Okay, so the anomaly of this August, this is the anomaly, and that is normalized by the variability, showed that you have a very highlighted East Asian subtropical front that marked by this dashed line. And the convective activity there is larger than 3 sigma. So it's very anomalous. Okay. So this had to do with a lot of things had to do later on in relation to this specific anomaly, specific activity. So now I want to come back to say, how did we sample both South Asian monsoon convection and the East Asian monsoon convection while we're flying over the Western Pacific? It's because we developed and implemented a specific diagnostic that is so successful that connected our sampling in the Western Pacific, which is somewhat downwind from the anticyclonic flow, bring in South Asian and East Asian monsoon convective top to us. So this, in a way, this diagnostic is really just a reverse domain feeling. You know, some of us in the past have done that and know what that is. Okay. So this work, you know, Ren Smith is about to submit a paper, and he said tomorrow, so maybe tomorrow he'll submit this paper, and in collaboration with them. So this is what it looked like. So we did all the flight. You can see the blue is a WB, light, cyan is a G5. This is our flight track. If you use back trajectory model to calculate where it came from, and this is from 30 days, but a lot of events happened within 5 days, okay? So if this trajectory encountered convective event based on the convective cloud database we have, and then you consider, you can map the sample you have done on the track to that cloud top, that encounter, to consider that's where the air mass brought from. You know, this works for, chemically works for most of the you know, medium to long-lived species. And so this specific figure is the frequency of occurrence of this encounter. So basically saying, if we look at all the track in every minute in the backwards, what is the distribution of where they encountered the convection and how often? So the interesting part is we have this red box, basically represent the East Asian monsoon, and this orange box, the South Asian monsoon. And the light up is the activity center. It's pretty much the convergent line and the monsoon trough. So that shows how physically this is working. So you have convection where you have the most convection, this happened, but you have the convection so persistent and so intense in the season. So we pretty much covered the whole range. Our sampling covered the whatever lofted up and brought to us. So I continue on this line, I'll explain more. So let's look at the convection a little more. So if you look at the convection from a convective cloud database we used for August, this left panel is the frequency of the deep convection, spatial frequency. So this pretty much light up the South Asian monsoon. So this large, high intensity of convection pretty much lined up with the monsoon trough and shows that the South Asian is the most potent, productive. But if you look at the right side, it's a different way to show this cloud product. That is, if you analyze the vertical distribution of the convective cloud top, and you look at the different percentile. So I have looked at all of them. So right now, I choose to use the 90th percentile. And you can see the potential temperature of that has a distribution that light up. There's a South Asian monsoon. What happened to my cursor? Okay, there's a South Asian monsoon and a 385 potential temperature, which is very, very deep. Then you have a really deep and intense East Asian monsoon for this season. Okay, so it turns out that the highest convection we saw in this entire month is here, the 395 and 18 kilometer in depth. Okay, the 395, sorry. And this location is on the eastern edge of the Tibetan Plateau. And there's a lot of detail about this event. It's not a one day, it's a month, how many people died, property, and all that related to extremely anomaly convection. But on the other hand, we have studied this monsoon, this behavior for multiple years. Every single year, including the dry run year, we always see deep convection event along the eastern edge of the Tibetan Plateau. So we used to think the southern edge of the Tibetan Plateau is the activity center. Now we know the eastern is. That's why in the past when we see, some people have seen that figure, I don't plan to show, is the carbon monoxide look like a mushroom. The mushroom have two stems. One is the southern edge, the other is the eastern edge. So I want to go more about this because it's really interesting. So let's look at what the reverse domain filling is doing. So on this figure on the left, this is a help from the WAS group. The WAS instrument from both plane, if you select their sample for CO greater than 150 ppTV, which is a very polluted air for those who are not familiar with chemistry. You don't see that every day on the ground, and even less on the 15 kilometer in the upper troposphere. So these are all the samples throughout the campaign on the flat track where they have seen triangles as a WB and the circles is a G5 and the other is WB. So then you use the RDF we just talked about to put them on the map. And their distribution is not random. So you see the gray, 4 patches of gray. These are the 4 clusters. Then they come with a reason. These 4 clusters are exactly located with these labeled high intensity of convection, deep convection. So all these red tone corresponding to convection deeper than 385 potential temperature. And this blue one, this cluster D, is 370, that corresponding to the color of the contour. But on the other hand, that one is in the region so north, so the background of tropopause is typically 360 K. So this convection at 370 K may as well be an overshooting convection. So this physical consistency of the potent air mass, the polluted air mass, high intensity of pollution, with the convective deep depth of the convection really demonstrate how effective this diagnostic is and how physical that is, the consistency. Yeah, this that is from Qinghai province in a county that they had two big events of 18-kilometer convection. So the last one, this is really related to the Asian monsoon convection used to be identified a lot lower, and I will say that later, but from our measurement, we identified much deeper convective transport. So this convective transport is shown by the top branch of the C shape. If you see the carbon monoxide and the dichromethane, these two species, you see the C shape. In ozone, you can see, if you see very low ozone at high altitude near tropos, that's because of the deep convection. So all species, in one way or the other, showed that the convective outflow came out very close to the tropopause and centered around 370 K, and some of the deeper ones go to higher, go to 380 K. This is how the convection, and some rare cases show that at 390 K, but mostly the center is about 370 K. So this convection a lot higher than our model is showing. Our model is not parameterized to do this. So because the deep convection and because the potent boundary layer, the first highlight we have identified, we have published this paper, is how East Asian monsoon delivers large abundance of very short-lived ozone-depleting substances to the lower stratosphere. So what this figure, this histogram is showing, without going through the detail, is, and the previous measurement has measured at the tropopause level how much the total ozone-depleting substances that had a shorter atmosphere lifetime than half year. And that's what they call the VSLS. So orange is what from ACCLIP. So orange shows that ACCLIP have seen a factor of 2 or more than the previous measurement. And the black region is the ozone assessment community. The latest assessment considered how much VSLs contribute. And based on the previous measurement from the tropical tropopause region, we can see how much more. So the next ozone assessment, these are going to be significant information. So in a different way, we can show a particular species called dichromethane, and this is from StratoClim and OMO, the two previous experiments largely sampled the South Asian monsoon outflow, and this is the ACCLIP. So this dashed line is the same place to help connecting to data with the different axes. So that shows how much more ACCLIP sampled, ACCLIP saw from the East Asian monsoon region. So this is now back catch up to say, what is dichromethane and why is the East Asian monsoon can be so significant? So dichromethane is the leading component of chlorinated VSL. So typically 70% of all different VSLs. So being a very short-lived species, they're not regulated by Montreal Protocol. There are a lot of times a replacement from the long-lived species like CFCs and HCFCs. They're controlled and regulated, but these ones are not. And there has been a significant increase because they're replacing the regulated ones. So in the recent decade, it has been shown the injection of these very short-lived species into the stratosphere has increased up to 50%. And these, from the modeling group, this increase has in some way started to show offsetting of the decrease of the long-lived species. So it has caused a lot of attention. And the Asian emission that is from both India and China showed up to be 68% of the total. So this is a surface emission map. This paper is published on Nature Communication 2021, showing the trend from Eastern China. So these are the emissions, and if you see the little purple triangle, I don't know how clear you can see that. Those are the factories producing this. And it's the first half of the decade, the last decade. It's the second half. The rate of increase is 13% a year. So that shows why we see it's not a surprise. It's a very large source right below the convection. So the next part, I want to go fairly quick to some other work without giving details. That in addition to, in connection to this transport, and we have a lot of work going on Asian monsoon aerosol layer. So this first line, I want to emphasize that the Asian monsoon aerosol layer has a distinct chemical signature that is a nitrate-rich. And in contrast to North America, which is sulfate dominant. So these work are going on. And I mentioned people leading paper only in a small fraction because there are a lot of paper going on. And so the other is to represent the nitrate, our model in the past do not have a good mechanism to represent nitrate. So even when we had a lot of ammonia, we know there's a lot of ammonia on the ground in Asia. And even had ammonia, it didn't have nitrate. So the recent progress is we meaning our team, and in this case, Yun Qian is the lead author of this paper, had worked out, implemented a new scheme to represent the nitrate, just published. So the other one is the black carbon. We have expected black carbon to be a low-hanging fruit, and because our model showed so much black carbon in Asian monsoon convection, but the data indicated a very large difference. So that suggests that we really have to revisit the scavenging, wide scavenging in our models. So that paper is in the process of moving to submission. The other one is the OCS. So OCS is an important component, important species for the stratosphere sulfur budget. So this work of Colin and others has shown Asian monsoon convection is a major source for stratosphere OCS. So this last one is the structure of this Asian monsoon aerosol layer. So in the past, our model have shown the Asian monsoon aerosol layer is centered on South Asian, and because the troposphere is higher, and when the tropos go to East Asian become lower, the monsoon aerosol will also have inclination. This data from ACCLIP airborne and from the nearby LiDAR from Japan. And there are a lot of little red crosses showing where tropos is. I suspect they're not very clear. But the idea is our data shows that the Asian monsoon under the large horizontal transport and shedding, the tropos is poorly defined. They are not effective. So the monsoon aerosol layer is extending at high altitude and getting into stratosphere and without being confined. So next one is about a few words about other species and chemistry. So it has been known that Asian monsoon can be important for UT NOx, especially both lightning from the storm and the vertical transport from polluted boundary layer will contribute to the UT NOx. So the ACCLIP data is an important evaluation data set for our model. So this is work of Jun Zhang in the audience, and that she has shown that our WACOM model represents the upper troposphere NOx really well as compared to ACCLIP data. And then this allowed her to further do an attribution study to see the source of NOx. How much is from lightning, how much from the transport. So this is also in the process to be submitted, and in a couple of weeks, I don't know. So she's working on this. And also the impact of Asian summer monsoon, large amount of NOx and VOCs will have impact on UT ozone chemistry. So this work is going on by Eleanor Waxman, also has a paper in progress. And at ACOM, our TOGA group is working on this large amount of VOCs from TOGA in the UT, and Becky has a paper in the work. And the convection, I have talked with recently in a meeting with some Chinese scientists measuring VOCs from the ground, try to do emission inventory, and they don't have even 10% of the species we have. So we can't, it's very hard to say how much is from the ground, and there's no ground measurement. So this data set is very valuable. There are other people asking, can we use this so we can compare with the ground data. So this is going on. And also there's a lot of work going on Asian monsoon, the role in stratosphere water vapor, and the study of clouds in the series formation and the particle formation. So a lot of work going on. So anyway, these are only a small fraction representative of what's ongoing. And after ACCLIP, we had, because the pandemic, ACCLIP was the first one after pandemic. Then there are many other campaigns went on into the field. People are trying to catch up. So a lot of people are really busy. They're trying to do data analysis at the same time. And so the publications are a lot is ongoing. So I had another problem. I moved to actual slide. I think maybe it's already a lot. And to leave some time for discussion, I'll move to, could be last slide if there's nobody asking for. But we had a lot of interesting understanding of how Asian monsoon tropopause structure is so unique. So that some other day, maybe I'll talk about that. So this is what is ongoing. We're developing an overview paper. And in this overview paper, we like to have a schematic to show what we have learned about Asian monsoon convective transport and what's so different from the past. So this is ongoing draft between me and Sean in progress for this paper. So you're seeing an imperfect one. So the basic idea is we know the anticyclone is centered at 150 hectopascal. And based on the analysis we have done on the convective cloud top, we know most of the convection are making into the center of the anticyclone level, and a lot of them are above the center level. So then east-west oscillation will, at this level, send them outside the confinement and to move to the rest of the world. Okay. So this is a different how. So 15 years ago, Mi Zhang and Bill had this paper based on a modeling, based on an ACOM model, had made this a very popular schematic, and it's popular for the next 2 decades on how the monsoon structure on the cyclone and convection, except the model convection is put the convection at 200 hectopascal below the anticyclone. Now that we know that's not right, and we also know our model very often is still doing that. I don't know all the models, but the model convective parameterization need improvement. That's what this last message is. I think ACCLIP, one of the message is it's very important to improve model representation of convective transport. And the convective transport community from chemistry need to work with the dynamic community where convection very often is about energy budget, it's about precipitation. And how would that kind of work be also true to the physics on the chemical transport is challenging. I myself worked hard to understand how they treat convection. When they treat convection, how the air mass is being considered. Are they just temperature, just mass, or do they have a content? So these are the issues. I hope in the next decade, maybe, that some progress can be made. I'll stop here.
Thanks, Laura, for that very interesting seminar. Quick reminder to those of you online, you can submit your questions in Slido. You'll find the box for that if you just scroll down your screen. Do we have any in-room questions?
Hey, Laura. It was a very nice talk. I really appreciate that. My question is, you showed the different modes of the anticyclone, the Iranian, the central, the Tibetan, and then the eastern mode, or however you call it, and that they move back and forth. That's probably driven by large-scale dynamics. What I'm curious about the source regions for all the short-lived species, do they move along with that somehow, or what would you imply also in the picture? I mean, the source regions, they're more or less stationary because that's where the emissions are, and then wherever the anticyclone is, it picks up what gets injected upwards into the anticyclone. Is that about right?
Yeah, so I'm trying to think how to explain that. So the idea is, I'll come back to this one. So the idea is, yeah, I'm back. So the idea is that there are two processes. One is a vertical process, it's convection uplifting. So that is centered over the Tibetan mode, which is not just over Tibet. You can see the range also oscillated really over the Asian continent. So when they are shedding out, is the process not quite back and forth. It's like really shedding out the piece from the main anticyclone, the air mass, from the center to east and west. So that's the second process, at the top of the convection. So that's why most of the source you were seeing is really from Asian continent. It's along this two activity center. So in the past, we saw most from the southern edge of the Tibetan Plateau. So it's like North India and the southern Tibet and the southern China. And at this time, we saw so much more from the eastern China. But they are really, yes, that convection. If I go to the ongoing schematic, you can see they're both in the anticyclone. Okay. The anticyclone large-scale oscillation to spread them around, even outside of those modes. Once the mode, they really mixed out to become part of global UTLS. Yeah.
Okay, thanks.
Yeah.
So looking forward, if you were going to go back to this region, would you try to sample something that's more of a shedding component, or would you go to the westward side and sample that part of the monsoon system if you only had one choice?
Well, I think going to west is very, very good. So first of all, we should first, now we have all this affiliates and all this campaign, we should have an integrated study to really identify what we have learned, what are the missing information. So the reason I think the West is important to have is because the anticyclone oscillation is not even. The eastern side is inclined. So the eastern side is on the lower side, the western side is on the higher side. So the sense is potentially if you're interested in the impact to stratosphere, knowing how much the western, what's the content of the westward shedding, and what's the altitude relative to the tropopause is important.
Okay. And one just comment on working with the people that develop the convective parameterizations, it's almost like a workshop in the making where we could bring together people from CGD and other places to start thinking about that. I don't know if you've reached out to them.
I haven't, when I was really dying to know that remember when we had a 79 level model that's flooding at the troposphere? You remember when before the campaign? I really was hoping to talk to someone. I think everybody's too busy, so when you think about that, they're thinking about something else, so I didn't get a response. So I think that passed to other people, maybe June and others, and Ren is working on SEMA and all this. Eventually, someone from chemistry community need to understand the convection. That's the problem. If we don't understand it, and you can also count on people from dynamic community understand the chemical transport. But yeah, there's a gap. Yeah.
Agreed.
Any other in-room questions?
Yeah, you talked about the trend in the very short-lived chlorine species that is going to reach all the way up, and you said that's a new information because you're saying that it's going to be transported up there. Did people before not take that part into account, that increase of the emissions? Is that not in the models? I don't know, actually.
Yeah, I don't know. These are a question maybe Eric has. Baruch had are working on these, the emission, and I know Qingliang is working on this too. So how well the transformer model is using up-to-date boundary layer emission? Is that what you're on VSLs?
No, you're saying that the models don't reach the convectively, they don't reach that high into the stratosphere. So that would imply that those species wouldn't get up into the stratosphere.
Yeah, that definitely will. That's why right now there's nobody shows the kind of transport we're seeing. No model showing that.
If that you don't see that in, yeah, okay. First of all, we have to model it and
right.
have it in the emissions, and then we have to see if we can see that trend
right.
also in the stratosphere.
Right. So right now the models are not seeing the convective outflow, the amount we're seeing. That is the problem, and the model, why is that happening, and how much is this bimodal, the two-mode, the shallow convection, deep convection, and what parameters they use to control the deep convection. These are the questions, at least I know I would ask, but I don't know how to answer that. Yeah, so someone has to be much more into it. And also, of course, now the new direction is go musical SEMA to adjust scale. So to have, in the region of monsoon, you actually don't do parameterization. You want to represent convection explicitly. So that's also the direction. There are many directions, and if we're motivated to make some progress, yeah.
I don't see any questions online, so while others are pondering, I'm curious. You mentioned that 2022 was obviously a pretty anomalous year, but that was kind of fortuitous for the observations we collected. Mm-hmm. Do you feel like there's anything you missed with it being an anomalous year?
Well, usually the question is not what we miss. Usually the question is how representative this is, how often this happens, right? So, well, I can't say that I wish they came out a little more often that we can actually see, because that's where we can access the airspace, right? But it's important to study because in the past we did not really analyze to see how well the East Asian monsoon convection is being represented and how often. This is anomalous because they moved really north and also delayed to August. Typically, that East Asian monsoon front is really along the Yangtze River, about 5-10 degrees south, and also stop by July, not go to August. So I think it's really important to actually analyze in a long time picture, what is the norm of East Asian monsoon transport? If there's someone interested in doing a project, that'll be very useful. Yeah.
Makes sense.
Yeah.
Holger?
One more question regarding observations. You mentioned the water vapor and ozone soundings on the Tibetan Plateau. How much more would more soundings help you even outside of campaign years if there were routine observations of water vapor and ozone in the lower stratosphere?
Yeah, I think those observations alone does have a unique angle to answer certain questions. For example, the long-term trend and so on. But the problem is if you're in particular location, typically they're in the southern flank, is in Lhasa or and Kathmandu and those places, is it's very hard to get a large picture of how that related to monsoon dynamic in a large scale. But still, I wish this year the problem was we have actually a long-term Chinese collaboration group and had obtained funding to do launch particle sound, a lot of particle sound from Tibetan Plateau that can potentially help us identify if there's a long-range transport source of that. What happened was because that year, the 2022, China had a very significant control on travel because of COVID. So that made it very difficult for them to actually go. Everybody goes somewhere, come back, quarantine for 2 weeks, right? So they can't really do. That's why the ideal situation is a better coordination between ground-based and airborne. That'll be much better. Yeah.
I was even thinking of expanding the network, not just one station somewhere in the Tibetan Plateau, but maybe some sounding sites in Japan, Taiwan, Korea, wherever it's feasible. So really span the entire region with soundings.
Yeah, it's difficult because the sensors are so expensive. The ground-based LiDAR group has done multiple years from Japan. So they have some, but on the other hand, ground-based LiDAR very much blocked by cloud. So their window opening, not very much. You can see one of the figures. So it's difficult. And I wish there are cheaper sensors. We can just, or drone operated, bring it back kind of thing.
Okay, thanks.
Thanks.
Thanks, Laura. So looking into the future, the monsoon system is going to change on the warming climate. And especially for 2022, you have strong rainfall convection over the East Asia region. Would you expect to see, for example, looking into the future, the measurement made by 2022, is that good representative for what you would expect to see in the future?
Yeah, I think that's a really good point you're making. That is when we say, very often people react to say, oh, the strong East Asian monsoon only happened once every 20 years or something like that. But the background is just what you're saying. The model study has shown both monsoons have trend. The global monsoon in different regions, but those trends are different under warming climate. So right now, the largest sensitivity with the climate change is the East Asian monsoon that had the largest increase with the greenhouse gas. So I think in some ways, our experiment provide alarm to say, this happened this year, but if there's an increasing trend, we'll make this process. We need to know how to model this process. I think that's potentially the message is out there, yeah.
Great. Well, thanks, Laura, for that comprehensive update. We'll be eagerly waiting for the papers that are soon to be submitted and under review. Let's thank Laura one more time for a great seminar.
Thank you. Thank you, everyone.